Good morning. My name is Murray Jones. This is a stick I found in my backyard. And this is the Coordinate Systems of Astronomy, presented rapid fire, all the important ones from the ground up, literally. This is the aforementioned ground. This is you, the observer. And this is a star that you might be observing. Now, if you're just sitting here on the ground, the simplest way to define which star it is that you're observing is simply by its angle above the horizon. We call this the elevation angle and term it theta. However, it is also possible that you might want to define the elevation relative to the vertical instead of relative to your somewhat lumpy horizon. So it might be cleaner to define it as this zenith distance, which is also an angle but measured to the vertical as opposed to the horizontal, and we term it z, like simply the complement of elevation angle. However, you, the observer, are not simply a two-dimensional entity. You are three-dimensional, at least I think you are. And that means that one parameter is not enough. You cannot simply say how high the star is, you also need to say which direction it is in relative to north. We call this direction the azimuth, and all that is a bearing from north around to the star that you're looking at, and then the elevation angle would be taken upwards from the horizon from there. And by horizon we do mean like an optimally flat horizon. We don't really consider the little bumpy hills and so forth. Now that is all well and good, however the Earth is not flat. So one must needs specify whereabouts they are on Earth, because if you are standing up here on the North Pole and looking over at this star here, you will have a very different azimuth and elevation angle to someone standing, say, here. So to specify where you are on Earth, we use a latitude and a longitude, which is your angle around from the city of Greenwich, England, where some Poms decided it would be a good idea to draw the prime meridian, which is in and of itself simply a fancy term for the spot where longitude is 0. However, the trouble with that is that Earth isn't actually spherical either. Earth is this weird, somewhat elliptical blob, which makes it relatively hard to simply define a latitude as the angle down from the pole, because you get two different answers. You can either define the geocentric latitude, which is the angle relative to the center of the Earth, or you can define a geodetic angle, which is based upon the angle of the surface of this elliptical blob at your current latitude. Neither of these options is necessarily better than the other, but it's very important to simply know which one you are using at any given point in time, because you will get different numbers out of them. The relation between the two is simply given by this inverse tan result, where the latitude in geodetic coordinates, those being the ones relative to the tangent of the surface of the Earth at your position, is simply the inverse tan of the tangent of the geocentric latitude towards the center of the Earth, divided by this 1 minus e squared, where this e parameter is the eccentricity of the elliptical blob that is the Earth. That is just a number, you can look it up. Now, what if we don't want to specify where on Earth we are, right? I don't want to tell you my latitude and longitude. I don't want to have to specify that every time I try and tell someone where my satellites are. In that case, we can use declination and right ascension. Declination is an angle upwards from the celestial equator, which is the equator of Earth projected onto the background stars. Right ascension is an angle around from the celestial meridian. Now, for the sake of completeness, as coordinates are not simply a spatial thing but must also be defined in terms of time, we can define the local sidereal time in terms of the right ascension and the current hour angle to give ourselves a temporal coordinate that is also based upon the rotation of Earth relative to the background stars instead of our specific geometry relative to the Sun. Now, that is all well and good if you're just hanging out here on Earth. However, what if I don't want to specify which planet I'm on? I want to be able to define the positions of various stars in the galaxy or the universe without having to say that, oh, I'm on Earth. I want it to be a generalized method that works if I'm on Mars or on the International Space Station or anywhere else in the solar system. In that case, we can abstract it one level further. We can take positions relative to the Sun. Now, thanks to some random Greeks, we call these heliocentric coordinates. And once again, it is simply a heliocentric latitude and longitude, this time taken but relative to a meridian that points toward the galactic center. This lets us very easily define the coordinates of anything that happens to be revolving around the sun. Now, what if we want to define the coordinates of something that instead of revolving around the sun is simply revolving around the center of our galaxy, which most of the interesting things are? In that case, we can quite simply define the radius from the center of the galaxy as well as a height vertically above the center of the galaxy, because our galaxy is a big flat dinner-shaped looking disk, which means it's quite convenient to simply find a radius out the disk and a height above or below the disk, and that gets us a very convenient coordinate, which is used in many things such as galactic dynamics modeling of the disk rotations and so on and so forth. Now, what if I don't want to specify that I'm in the Milky Way galaxy? Well, let's zoom out a notch. We can define coordinates relative to our local galactic cluster. Now, the galaxies throughout the observable universe tend to be clustered in little blobs. That's largely thanks to gravity, and we can relatively simply define the center of one of those blobs. Based upon a simple center of mass equation, this is simply a weighted sum of all of the objects that you choose to include in the blob, and that gives us a center of mass position. From there, we can define a plane through the center of mass, and define even Cartesian coordinates if you want to based upon that plane. These are called barycentric coordinates, as these components whose masses we are summing up is the baryon comprised matter of the local galactic cluster. We're not generally summing up the dark matter component because it's dark and we cannot see it. Now let's zoom out a notch further to the entire observable universe. This is everything that we can see with our telescopes, and to the absolute fascination of astronomers, we see all these threads. All the galaxies throughout the universe are clustered into these threads over gargantuan cosmic scales. Now these scales are so gargantuan that it actually takes light an extremely long time to travel through them, meaning that what we actually observe is these distant galaxies in a state as they were many hundreds, if not thousands or millions or billions of years ago. That look-back time, as it is termed, is defined here as TL, the integral over the inverse of 1 plus the observed redshift times the Hubble parameter. Now, the redshift is the primary method by which we conclude one of the most important results in astronomy, and that is that space itself is expanding, which is a bit of a weird concept to think about, but that's what's happening. Either that or space itself is red. The data is actually consistent with both conclusions, but astronomers generally prefer the conclusion that space itself is expanding, and that this redshift is caused by the photons themselves getting stretched out as the space that they move through expands, much like a beach ball being inflated. What's inflating it? Dark energy. What's dark energy? We have no idea. But the important part is that we're able to define a redshift Z by the simple relation that 1 plus the redshift is the observed frequency divided by the emitted frequency, which we can tell by comparing the known spectral signatures from a laboratory measurement to the shifted ones observed from distant stars and galaxies. We can also relate this to a scale parameter at T0, the time of the observation, and TE, the time of the light emission. That's redshift, this is look-back time, and the Hubble parameter, or as Edward Hubble proposed it, the Hubble constant, only for it to turn out to not be constant. Hence Hubble parameter. We quite simply define that in terms of a measured expansion rate today, multiplied by the square root of all these redshift-dependent terms, scaled by the densities of matter, radiation, dark matter, and the curvature of the universe, respectively. The curvature of the universe is quite typically set to -1 by general agreement of astronomers, because that's what fits the data. That does end up giving us a rather unintuitive hyperbolic geometry instead of a nice sphere that a curvature of +1 would give us, but the data saith that that be correct, so that is what we roll with. Now you might be thinking, we've just talked about the observable universe, so can we zoom out any further? And the answer is, yes we can. This is the cosmic microwave background dipole, which was discovered by some people who were trying to make their radio antenna work, and originally thought that what they were detecting was the radio emissions of pigeon poop, but it turned out that after they cleaned the pigeon poop, it was still there, and they had in fact discovered the cosmic microwave background. Now this background is in fact a dipole, because Earth is moving through space really quite quickly. Hence the cosmic microwave background that we see in one direction is blue shifted relative to the light that we see in the other direction when looking away from that direction of motion. This is what that dipole looks like. And this is how we can define it in terms of the thermal difference across the dipole, the velocity of Earth's motion, and the speed of light. Now, once you subtract the dipole effects out of the cosmic microwave background, that is when you get this pretty picture that you've probably seen before. This pretty picture is probably the closest thing we're ever going to get to a photograph of the Big Bang itself. And it shows the fluctuations in temperature across the very early universe. It shows the asymmetries that led to the formation of structure that we see today. It led to our existence, really. You could call this, and many people have called it, the blueprint of the universe, which is a pretty poor name because a blueprint should fully define something, whereas this kind of just hints at asymmetries that mean something gets defined, but you get the picture. Let's zoom further out to the universe as a whole, and this slide is basically a cosmology course in 30 seconds. We have the Friedmann-Lemaitre-Robinson-Walker metric, which defines a space-time interval ds squared, which gives us essentially the geometry of the universe in terms of k, our curvature, an r squared co-moving distance metric, which essentially is a coordinate that expands with the universe, the theta and phi angular coordinate, the a scale parameter that we mentioned earlier, and of course the minus term for the speed of light time term that you've probably either seen or will see in relativity class. We also have the Friedmann equation, which is what relates the square of our Hubble parameter. Remember the expansion rate A dot on A, this is just the Hubble parameter right here being squared, and we can relate that to the gravitational constant, the density of the universe, the curvature parameter, the scale parameter, a dark energy term, and the speed of light squared. From this we get the three important measures of distance used in cosmology. The co-moving distance, here defined in terms of redshift, and the Hubble parameter, which is a distance that does not change as the universe expands. If you've seen the demo with the balloon being inflated, that's simply where the dots are drawn on the balloon. We have the luminosity distance, which will reduce as the universe expands because the intensity of the light received from distant objects reduces as they recede. And we have the angular diameter distance, which relates to the apparent shrinking of distant objects as the universe expands and they recede from us. Again, these are relatively complex expressions, although expressed simply through other complex terms. And the reason that they are complex is because, once again, of that inconvenient fact that the Hubble constant is not constant. And that is a rapid-fire overview of the coordinate systems in astronomy. I will not be taking questions because this is a pre-recorded YouTube video. Have a nice day.